السلام عليكم ورحمة الله وبركاته. أرحب بكم جميعا في اليوم الثاني من فعالية ابن الهيثم والضوء، وذلك ضمن فعاليات واحتفالات دولتنا الغالية قطر وهيئة اليونسكو بعام 2015 كسنة العالمية للضوء، بمناسبة مرور 1000 عام على إصدار كتاب المناظر للعالم العربي الجليل أبي علي الحسن ابن الهيثم، وإعلاء لشأن العلم والعلماء العرب، واحتفالا بالسنة العالمية للضوء. حرصنا جميعا على تنظيم هذه الفعالية، والتي بدأنا أمس واليوم يوم الأخير على هامش مؤتمر الضوئيات في الشرق الأوسط لعام 2015. ونشكر اللجنة المنظمة لاستضافة هذه الفعالية، وأيضا نشكر شركائنا الصندوق القطري والمجلس الأعلى للتعليم ومركز السدرة للطب والبحوث وجامعة قطر وجامعة تكساس وسفارة الولايات المتحدة في دولة قطر. وسوف أسرد لكم فقرات اليوم الثاني. الفقرة الأولى لمحاضرة لعالم الفيزياء وولفغانغ كيترلي، نرحب فيه أولا الجميع، نرحب في العالم. والعالم وولفغانغ هو الحائز على جائزة نوبل للفيزياء في عام 2001 حول الاستخدام الأكثر برودة للضوء وكيفية تكوين أكثر مواد برودة في الكون. وبعد ذلك سوف نعيش أيضا مثل يوم غد مع مستر توماس الذي فعلا كان يعني amazing yesterday. فراح نعيش activities عندك مثل مع الطلاب إن شاء الله. واخيرا هناك كلمه للدكتوره الفاضله دكتور إلهام القرطاوي في الختام ان شاء الله. فالان ارحب بدكتور بلك، ولكم دكتور بلك، وبعد ذلك هو راح يقدم البروفيسور بورغي. Thank you.
Ladies and gentlemen, dear guests, welcome. Good morning to all of you. It's my privilege, great honor to introduce Professor Wolfgang Ketterle, and in order not to miss any of the important information, I'll just read it. So, Dr. Wolfgang Ketterle has been the John D. MacArthur Professor of Physics at MIT since 1998. He leads a research group exploring new forms of matter for ultra-cold atoms, in particular novel aspects of superfluidity, coherence, and correlations in many body systems. His observation of Bose-Einstein condensation in a gas in 1995 and the first realization of an atom laser in 1997 were recognized with the Nobel Prize in Physics in 2001, together with Professor Eric Cornell and Carl Wieman. He received master's degree from the Technical University of Munich in 1982 and a PhD in physics from the University of Munich in 1986. And that was the time, I believe, I met Professor Ketterle for the first time. He did postdoctoral work at the Max Planck Institute for Quantum Optics in Garching and at the University of Heidelberg. In 1990, he came to MIT as a postdoc first, and then joined the physics faculty in 1993. Since 2006, he is the director of the Center of Ultra-Cold Atoms, an NSF-funded research center, and associate director of the Research Laboratory of Electronics. His honors include the Rabi Prize of the American Physical Society in 1997, the Gustav Hertz Prize of the German Physical Society in 1997, the Fritz London Prize in Low Temperature Physics in 1999, the Danny Heinemann Prize of the Academy of Sciences, Göttingen in Germany in 1999, the Benjamin Franklin Medal in Physics in 2000, the Non-Commander's Cross with Badge and Star of the Order of Merit of the Federal Republic of Germany in 2002, the MIT Killian Award 2004, and a Humboldt Research Award in 2009, and membership in several academies of sciences. He holds honorary degrees from Gustavus Adolphus College, St. Peter in 2005, the University of Connecticut in 2007, Ohio State University in 2007, and Strathclyde University in 2011, and also an honorary professorship of the Northwestern Polytechnical University in Xi'an, China, from 2014. Dr. Ketterle, please.
Good. So, good morning, everybody. I think we are all here to celebrate light. And we all know that how much light means to us. I got up this morning at 6 o'clock and I was out at the Corniche and I saw the sunrise. Light is beautiful. Light is also a form of energy. But what I want to talk today about to you is that light has also one other property. It's a force. It has momentum. You can push things around with light. Which has enabled me to push frontiers in science is the fact that light is also a force. You can push things around, you can accelerate and slow down particles with light. So that's what I want to talk to you about. And the fact that light is a force, that light has mechanical effects, was already realized by Johannes Kepler, and I'm not sure if you can read Latin numbers. This book is in the year 1619, 400 years ago, and this is when Kepler realized that the tails of comets always point away from the sun. Well, it feels a little bit more subtle. Comets can have two tails, and there is one tail which consists of charged or ionized particles, and this is deflected by the solar wind, which is a flow of charged particles, so it's not the light. But then there is a second tail, a dust trail, and this is pushed by sunlight. So it is this trail here, this tail, which is pushed away from the sun by sunlight. So how big is this force of light? Well, let's just talk about energy. We know that solar energy is very important, and we often use solar panels to convert solar energy into electricity. And actually the amount of energy which comes from the sun is really substantial. 1 square meter of area collects 1 kilowatt of power. And 1 kilowatt is a lot. You can have a space heater or a refrigerator can run with 1 kilowatt. So this is the energy received by a solar panel. But now let me ask you, if you have a solar panel and you receive the energy from the sun, the solar panel also receives a force. Do you know how big this force is? A lot of people do research with photons. They don't know how big the force is. Well, let me tell you. We know that the energy is related to the frequency of light with Planck's quantum, and then if we divide by the speed of light, we get the momentum. So it's very easy. It's just one formula involving Planck's quantum, and what you find out is that the pressure on the solar panel is 5 micronewton per square meter. So that means the force experienced by the solar panel is as large as the weight of a grain of very fine sand. Hard to measure, but important. You can observe it in the deflection of comets. And we are using it in our research on cooling particles to ultra-low temperature. So let me now make a step and say we have this force of light, and we want to apply this force of light to atoms, to neutral atoms. So let me now explain it to you. We know that light is an electromagnetic wave. And actually, with the year of the light, we celebrate 1,000 years of Ibn al-Haytham's accomplishment, the Book of Optics, but we are also celebrating 50 years of Maxwell, the Maxwell's equation, and an understanding that light is nothing else than electromagnetic wave. So if electromagnetic waves, electric and magnetic fields, exert forces only on charged particles. So let me now explain to you how light can push around neutral particles. And the story goes, well, let me first demonstrate to you what a magnetic field does. If you have an electron beam in a vacuum chamber and there's a little bit of air in it so you can see it, and then if you put a magnetic field on it, the magnetic field is deflecting charged particles. That's called the Lorentz force, and most of you must have heard about it. Okay, so the story is the following. If you have a neutral atom and you apply an electric field, then you separate the positive and negative charges. You create a dipole. And if you have light, which is an electric field going back and forth, you create an oscillating dipole. So the electric part of the light creates an oscillating dipole, which is a current, and then once you have an electric current, the magnetic field of the electromagnetic wave can deflect the current via the Lorentz force. So in other words, the microscopic origin of the fact that neutral atoms experience a force due to light is a combination of the electric field creating a current and the current being deflected by the Lorentz force. So how can we observe this force of light? Let me give you two examples where the effect is not due to the force of light. And you may have seen this kind of, it's a toy, but it's also a wonderful scientific demonstration. It's called a light mill. If you expose this device to light, those pedals, it looks like a sail, moves around, rotates. And the question is that due to the force of the photons? Well, the answer is no, because you would expect that if photons are reflected off the reflective surface, then you get 2 times the momentum of the photon, whereas on the black surface, when photons get stuck, you only get 1 time the recoil of the photon. So you would actually expect this device to rotate in such a way that the silver side moves away from the light. If you look at this device, it moves in the opposite way, because it's a thermal effect. The light is heating up the black part, and then on the black side, you have faster air molecules because they are hotter and they provide extra recoil. So when you see those devices, it's a thermal effect, it's an effect of the energy of light, but not of the force. Or people try to do fusion as an energy source, have a fusion reactor, and in one approach, you take a pellet and you compress the pellet to high densities by using the world's most powerful lasers. But this effect, where you compress something with laser light, is again a thermal effect. You heat things from the outside, and then fast thermal particles move outside, and the recoil of the thermal motion compresses the pellet. So these are effects where it is not the force of light, but the energy of light which causes mechanical motion. But let me now switch to the area of my research, and these are neutral atoms. When we have neutral atoms, and we create neutral atoms by having an oven or reservoir, and atoms just effuse into a vacuum chamber. So now we have a beam of neutral atoms, and if we use a laser beam and counter-propagate the laser beam with the neutral atom, then these neutral atoms slow down, they are decelerated. And they are decelerated exactly by the force I described to you, the mechanical force of light. And this deceleration, now comes the point, the deceleration is very fast, 10 to the 5G. That's 10,000 times stronger deceleration than you would maybe have in 5G. Well, it just tells you what is huge for human beings, G, is actually rather small for atoms, for small particles. Or in other words, the light force, which I described to you, was small for solar panel. Do you remember the weight of a grain of sand? But if you apply this force to a neutral atom, it causes a lot of deceleration because the neutral atom has only a tiny mass. So that's why we can, using the radiation pressure force of light, why we can decelerate atomic particles with 10 to the 5G. And that means we have now an oven, we have a thermal particle which moves at 500 meters per second, the speed of a jet airplane. And after 1 meter in our laboratory, those particles come to a standstill. So that's how we make particles very, very slow. Let me now explain to you how we can use laser light not just to slow down particles, but to reach very low temperature. So in the first step, we created some slow atoms, and now we irradiate them with laser light. So what you have to understand is that when atoms are irradiated with laser light, most people think if you shine a powerful laser onto matter, the matter gets hot because of the energy. But atoms are very special. When atoms absorb a photon, they go to an electronically excited state, and they, within millions of a fraction of a millionth of a second, they have to emit the photon and go down. So in other words, atoms cannot absorb the energy of the photon, they have to re-emit the photon immediately. So therefore, energy in, energy out. So the only way how atoms change their energy is if you look at the color of the light. If the color of the emitted light is blue-hued, if the photons which are re-emitted are a little bit more energetic than the photons of the laser beam, then the atom loses energy by scattering light. You say, wow, the light changes color? That's complicated. But it's not. It's an effect as simple as the Doppler effect, which can account for it. Let me explain. I think you're all familiar with the Doppler effect. We usually experience the Doppler effect when we have sound and moving objects. In the old days, I would have said, well, if there is a train and the train has a whistle, but not so many people experience trains anymore, and also those trains don't have whistles anymore. But let's take an ambulance car. If an ambulance car is driving towards you, or when it's driving away from it, you hear a different pitch of the sound. Here, the sound is higher frequency, and here the sound is lower frequency because of the motion of the ambulance car. So we can now exploit that with atoms. The laser light we use to illuminate the atoms is red-hued. It doesn't have enough energy to excite the atom, unless the atom moves towards the light, and then this Doppler shift shifts the laser light into resonance. So it is the motion of the atom which allows the atom to absorb the photon, but then it emits the photon into all directions randomly, where positive and negative Doppler shifts cancel each other. So it is simply this Doppler effect which you can experience with an ambulance car, which makes an atom absorb light, which is missing some energy compared to the resonance, but then the emission is on resonance on average. So here you have an effect
where an atom absorbs and emits light, and every time it scatters a photon, it emits a little bit of its energy. And this energy is taken away from the motion, from the temperature of the atom. Now, isn't that beautiful and subtle at the same time? It means you irradiate atoms with laser light, and the atoms get colder and colder and colder. Very counterintuitive. Well, it's pretty cool, I think. And you can actually see it in action now in hundreds of laboratories around the world. If you have some sodium vapor and we use yellow light for sodium, you observe this fuzzy cloud of atoms, and these are atoms which are 1,000 times colder than interstellar space, millikelvin temperature. Or here you see another color, that's red, that's lithium, the same effect. Laser light is used to cool atoms to temperatures much colder than interstellar space. Now, what I said, it looks so simple now. It needed really some insight, and it was those phenomena, the phenomenon of laser cooling, was discovered by those and other people, and for the accomplishment of laser cooling, the Nobel Prize in 1997 was given. Now, what are cold atoms good for? Well, I will tell you that they're wonderful for research, but they also have practical applications, for instance, for atomic clocks. You know that the global positioning system and worldwide communication and worldwide navigation requires very, very accurate timekeeping. And the most accurate clocks are atomic clocks, because they don't have gears and mechanics. There is something moving in an atom, and it always moves at the same frequency, whether this atom is in Qatar, in Germany, or United States. So we use atomic oscillators as clocks. But the fact now is, if an atom moves fast, it's like we have a watch, and you have to read very, very quickly. The precision is limited. And conventional atomic beam clocks, as they were used for many, many decades, have atoms which move at 100 meters per second, almost at the speed of an airplane. But now, using laser cooling, what I just described to you, we have now atoms which move in an atomic fountain at this, pretty much at the speed of my hand, which is 1,000 times slower. And well, if you have 1,000 times more time to read on your wristwatch, your reading time with 1,000 times higher precision. So to slow down the motion of atoms has provided us with major advances in metrology and timekeeping. Okay, so let me now come to the next step. This laser cooling is, yes, pretty cool. It takes atoms down to milli and microkelvin temperature. But now I want to tell you about what happened in my laboratories 20 years ago, and eventually I received the Nobel Prize for it, because I was able to go even further to absolute zero. So we wanted to get atoms even colder, and I will tell you in a moment why, but let me first describe to you how we did that. At some point, laser cooling cools the atoms to a certain temperature, but then you reach a limit, which is actually related to the photon nature. I don't want to go into details here, but we need now a second refrigeration scheme to go to lower temperature. And we do it in the following way. After the atoms are slowed down, cooled by laser light, we switch off the laser light, and we hold on to the atoms with magnets. Many atoms are magnetic. They have an electron which is like a compass needle. It's like a tiny little magnet. And by putting big magnets around it, we can make the atoms confine the atoms in magnetic fields. We call it a magnetic trap. It's a little bit like you have a cloud of atoms, and you have built a container around it, but the container is made of invisible magnetic fields. It's magnetic walls, magnetic confinement. Okay, so once we have the atoms in this magnetic container, we have to cool them. And let me tell you how we cool them. So we need atoms. That's now, here the analogy is coffee. We need a container, we have a magnetic container. Here it's a cup. And now we have to cool it. And you know, if you want to cool a cup of coffee, you may just blow at the cup of coffee, blow it out, blow at it, and make it colder. And what you do here is, you actually cool the coffee by evaporation. Coffee cools down, well, for a number of reasons, but one reason is that when coffee is hot, you see some steam above the coffee. But the steam are the most energetic water molecules which had enough energy to leave the water. So if the most energetic molecules leave, those which stay behind have less energy, and that means lower temperature. So evaporation is the way to cool something down. And if you force the evaporation by blowing at it, it goes even faster. Well, and now I hope you understand how we reach the lowest temperatures ever achieved, and this is by evaporative cooling. We have ultra-cold atoms in a container, magnetic flak, and then we blow at them. Well, we blow at them with microwaves and radio waves, but you got the analogy. We blow at them, and this is how we force evaporative cooling to take us down to nano-Kelvin temperature. So when we reached nano-Kelvin temperature, there was one big discovery we made, and this was the Bose-Einstein condensate. So in that sense, I was lucky. I was, you can say, in some of the most creative years of my life, I was building refrigerators. Well, not the common refrigerators. I told you, the laser refrigerator, the evaporative cooling refrigerator, using all the kind of things we have learned in atomic physics and applying them to the goal to reach the lowest temperature in the universe. And when we cool down gases to low temperature, there was a special form of matter which was famous. Well, everything which Einstein did is famous, and if something has Einstein's name, people think it's important, and probably it is really important. And so what we were able to discover at low temperature was this Bose-Einstein condensate, which people have speculated about for many, many decades, but it was only now that we had the low temperature to observe them. Actually, since this is a mixed audience, let me just kind of give you an analogy. I want you to make sure that you understand why low temperature is always good to make this kind of things. I mean, here in Qatar it's really hot. And I would say, unless you travel the world, you would never experience ice and snow. Unless you have a refrigerator. If you put water into a refrigerator, you open the door to the refrigerator, suddenly you observe something which has not existed naturally, at least not in this region of the world. And then you look at it and you see something which nobody else has seen before. And this is pretty much what happened to us. We found a way to refrigerate atoms to nano-Kelvin temperature, lower than anybody else. And now I want to sort of tell you what happened when we opened the door of the refrigerator. When we looked what was inside, we found something which was unique, the Bose-Einstein condensate. So whenever you reach lower temperature, you can find forms of matter which have not existed before, which nobody has seen before. And the form of matter I want to describe is that when atoms slow down and get colder and colder, there is this phase transition to Bose-Einstein condensation that suddenly, and this is shown here in this cartoon, the atoms are not moving randomly around anymore, they start to march in lockstep. And this marching in lockstep, it's actually a metaphor for superfluidity and superconductivity. This marching in lockstep is a new form of matter. It's actually a form of matter. The marching in lockstep comes because all the atoms no longer have the individual identity. They are all in the same quantum state. They all form one big wave. So I do like cartoons, and I think this cartoon is really beautiful. And actually, look at those faces. They are absolutely identical. If atoms were not absolutely identical, they couldn't form a wave. This is quantum indistinguishability. So the artist here has captured a lot of important physics in this drawing. But when it comes to the Bose-Einstein condensate, you cannot see the phases anymore because everything has become one big matter wave. So let me tell you how we were able to cool down atoms to those very low temperature and then observe the Bose-Einstein condensate. So that brings me to the question, if you're very, very low temperature, how do you measure? Well, we know that we measure temperatures with a thermometer, but I can tell you there is no thermometer which you can buy and which works at micro and nanochemical temperature. So if you really go back to basics, what temperature is, at its most basic definition, is a measure for the energy of matter. And when it comes to an atomic gas, the energy is motion, it's kinetic energy. So if we simply measure the thermal motion, how atoms move around in the gas, that's how we can measure the temperature absolutely. And that's done in the following way. If we take those very cold atoms, they are confined by magnetic fields, but then we switch off the magnetic fields, so now these atoms just fall down. But also because they are in motion, they spread out. This is shown here. If we now look at the size of the cloud, and we simply take a picture of those atoms by illuminating them with laser light, then they cast a shadow, and with a digital camera, we take a picture of the shadow. Then we can now determine the temperature. If this shadow is 2 times larger, the atoms move 2 times faster, and that means the kinetic energy is 4 times higher, the temperature is 4 times higher. It's really as easy as I tell you. So let me now show you what happens when we take those shadow pictures. We have a cloud of atoms, laser cooling, evaporative cooling, we cool it down. Then we switch things off, the cloud expands, we take a picture. And those atoms, they hit the walls of our vacuum chamber, our pumps take care of them, those atoms have done their job. But now we cool them to lower temperature, and when we look at the shadow is smaller. And we do it again and again, and I want to show you now what happens. So this is the frequency of the radio frequency, we blow at the atoms, so we cool them further, and you see how the shadow shrinks. But it's not just shrinking. We suddenly realize there is something inside. It's like a pit in a mango, a pit in a cherry. And you also realize this is sort of oblong, whereas the cloud was first spherical. So something has happened. And it was really this observation which was the discovery of Bose-Einstein condensation. This round cloud are the atoms which randomly move in all directions. But then suddenly there is a new quality. There are those atoms which they are not spreading out anymore. They are very, very cold. The coldest band in the universe. But also they have a different physical property because they are elongated, whereas the normal cloud is random. Everything moves randomly in all directions. I don't want to go too much into details, but the fact that the cloud is oblong shows that these atoms are now one big wave, and because we have used an elongated magnetic container, the cloud now looks elongated. But without going into any details, you see with the naked eye that something has happened here. And this was the phase transition to Bose-Einstein condensation. Anyway, I don't want to talk to you about all this 20 years of exciting research we could do with Bose-Einstein condensation. I would rather like to keep the focus on light, because today we celebrate light. So let me come back to light, and sure, you will still see some pictures of Bose-Einstein condensate, but what I really want to emphasize is how we can use light as a tool. And the question I want to address right now is, how can we shape atomic matter, atomic clouds, using laser light? So in other words, we have this cloud of ultra-cold atoms, and for me, those ultra-cold atoms are now like Lego pieces, and we want to assemble them, we want to put them into new situations, make them behave in a very new and interesting way and study it. But how do we make them behave in a that uses light again. So I mentioned that light is the way how we communicate with the atoms, how we push them, how we put momentum on them and apply forces. So let me now explain to you, which has now become the most important tool in my research, how we use laser lights to put the atoms into all different kinds of shapes. I've already mentioned to you that the fact that atoms, neutral atoms, experience forces from electromagnetic fields is related to the fact that the electric part of the electromagnetic wave is creating an oscillating dipole or oscillating current. And I explained to you how laser cooling happens by that these oscillating currents experience a Lorentz force. Well, now I have to tell you something else. When we take the laser frequency and move it far away from the atomic resonance, the atoms experience a force, but the force is a different force, which can actually have two sides, positive or negative. And let me explain it. If you have an electric field and it shakes a dipole in the atoms, positive, negative charge, there are two regimes. And I can demonstrate that here with the rubber band and this bottle. If the frequency is slow, my hand and the bottle move in phase. Both move up and down together. But if I do it faster, you see that my hand and the bottle move in the opposite direction. If my hand goes down, the bottle goes up, and vice versa. So what you have seen here is that there is a change of sign from moving together to moving opposite to each other when I change the frequency. And this is now what we can exploit with neutral atoms. If we shake the dipole with an electric field at low frequency, the dipole is plus the electric field, it follows the electric field, but at high frequency it has a minus sign. And the fact is, since the energy is related to the dipole times the electric field, the sign enters the equation, and that means that the atoms, when the frequency of the light is low, are attracted by the light, whereas at high frequency, when we get the minus sign, which I demonstrated to you, the atoms are repelled by the light. So we have now, just using laser beams, the way to push the atoms or to repel the atoms. And that can be now used in many ways. Here I'm just trying to give you an analogy for that. You're all familiar with magnets, and usually when you take a piece of iron, iron is attracted by the magnet. This is called paramagnetic. But there are some substances, graphite for instance, or bismuth, which have the opposite effect. They are diamagnetic. If you would hold them close to a magnet, they would be repelled by the magnet. The effect is weak, and usually when our children play with this kind of magnetic materials, and usually not with those kinds. And what I pretty much told you now is, depending on the frequency of the laser, the atom behaves in a paraelectric way or here in a dielectric way, and this is described by the dielectric constant. So here you see examples now how we can shape atomic matter. If you use one laser beam and it attracts the atoms now form a small elongated cloud like a spaghetti. If you take two laser beams, the atoms form what looks like a cross. So that's how we can shape atoms. Or if we use the opposite force, we have used that this was actually one of the most important experiments I did, which was mentioned by the Nobel Committee. When we had one Bose-Einstein condensate, we used a laser knife, we were cutting it into two pieces by using the repulsive action of light. So now we have two Bose-Einstein condensate, and we could show an interference pattern which demonstrated the coherent nature of the Bose-Einstein condensate. And actually, what I just described for you, to take a Bose-Einstein condensate and cut it with a knife, this is shown on my Nobel diploma. When you go to Stockholm and receive the Nobel Prize, well, it's a fantastic week of celebration. And the Swedes, for 100 years, they have perfectionized the way how they do honor to scientists. You are in a nice hotel, you have a driver for the whole week with a nice limousine, you are invited for dinner with the king and queen, you got a Nobel medal, which is a nice gold medal. But what is really special is your Nobel diploma is a piece of art, drawn by an artist. And my Nobel diploma shows the power of light. You have a Bose-Einstein condensate, and this is the laser knife which cuts the Bose-Einstein condensate. And you remember this laser beam is at high frequency, because at high frequency you have this negative sign which I demonstrated to you with the water vapor. And this is how we can split the Bose-Einstein condensate into two. So I've tried to give you two examples how we can shape atoms with attractive and repulsive forces. Let me give you one other example which actually plays an important role in our current research. And that is, we want to use Bose-Einstein condensates to study, to provide, to obtain a deeper understanding for materials. In other words, we use Bose-Einstein condensates not like we use the atoms which come from Bose-Einstein condensate like Lego pieces. We assemble them and then we study them. And you know that many materials in nature come in the form of crystals. Metals have a crystalline structure, silicon has a crystalline structure, and we want to use now those Lego pieces, these ultra-cold atoms, to learn more about crystalline materials. So let me now tell you, how can we use laser light to create a crystal out of very cold atoms? Well, this is a beautiful crystal, quartz crystal, and we're not trying to immediately go to this kind of complexity. What we want to do is, we want to first use simpler crystal arrangements, and the simplest one is what comes in the form of table salt. It's a cubic lattice. So how do we make it? Well, if we use two laser beams, and the two laser beams interfere, they form a standing wave. When you have two laser beams which counter-propagate, they form a pattern where the electric field is high, low, high, low. You know already that if the laser frequency is low, the atoms are attracted to the high field. So the atoms want to go where the field is high. We can add two laser beams in the other direction, and then the potential landscape observed by the atoms looks like an egg carton. The bottom of the egg carton, that's where the atoms want to be, like the eggs, that's where the electric field is highest. So by using two pairs of laser beams, we actually create an egg carton for atoms, and when we put in the atoms, they arrange themselves in a crystalline way. And I think it's obvious that you can extend it even to 3 dimensions if you want. So this is a direct observation of that done by my colleagues at Harvard. They have created this situation, they've put in some atoms, and now using an optical microscope, you can observe the atoms. Each dot is a single atom, and you see that they're really arranged in the pattern of an egg carton. You would say, okay, well, what can you do with that? Well, it gets more interesting when you have one egg or one atom per side, and you try to put in a second one. Well, eggs repel each other, but atoms may not repel each other, and so you may have a situation where you can have multiple atoms per side, but if the atoms strongly repel each other, they only want to be one atom per side. And what I just described to you You may think it's just playing with eggs, but this is quantum mechanics. The particles move from side to side by quantum mechanical tunneling. They propagate like waves. And what I described to you, a situation where you may have multiple atoms per side, to this situation is a famous quantum phase transition where we learn a lot about the nature of quantum phase transition by studying it. And this transition from kind of random numbers or different numbers, fluctuating numbers per side, to this very orderly phase, hundreds or even thousands of scientific papers have written about that. And now, using light as a tool and alpha-cold atoms, we can realize that in the laboratory study. Okay, so I'm getting towards the end of my talk. And there's one more thing I want to explain to you. I showed you that light is a powerful tool. Light is a source of energy, but in our research, we are really harnessing a property of light which most people don't experience, and that is light is a force. And the force can be used for slowing atoms, cooling atoms, and the last thing I told you, for shaking atoms, forming a crystal of atoms and such. But let me now also say that light is an inspiration. Light comes in a very special form, and that's light. We have ordinary light and we have laser light. But this is the property of electromagnetic waves. The Bose-Einstein condensate is a matter wave. The Bose-Einstein condensate is for atoms, what the laser light is for light. So we can now try to get inspired by light and do things with atomic matter waves, which have been done with electromagnetic waves before. So the first thing which may come to your mind is, if you think you have control now over matter waves, you can make coherent matter waves, you want to explore the analogy with laser beams. So these is here a gallery of pulsed and continuous beams, but it's not beams of laser light, it is beams of matter waves. So what you have here is a coherent stream of atoms of matter waves in full analogy to the optical laser, which is a coherent stream of photons. Another important aspect, of course, of the optical laser is the optical laser is based on amplification. If you take a laser beam and send it through an active medium, what you can get out of it is a stronger laser beam, a more intense laser beam. And it is this principle of stimulation, of optical amplification, which makes a laser work. So what we actually demonstrated, inspired by light, inspired by the laser, was an amplifier for atoms, a matter wave amplifier. You would say, well, how can you amplify atoms? Let me tell you. So what we have is, we have a Bose-Einstein condensate, and we have a small cloud of atoms. And this small cloud of atoms moves through the Bose-Einstein condensate. How do we create a small cloud of atoms? We snip something off from the Bose-Einstein condensate. How do we make it move? We use the force of laser light. So we use all the tricks I've told you in various combinations now, but let me not go into the details. So we have a small cloud of atoms. It moves through the Bose-Einstein condensate. And atomic amplification now means that the cloud which comes out is bigger. And it's not that we have created new atoms out of nothing. What happens is that atoms from the Bose-Einstein condensate have amplified the atoms which go through it. A laser beam does not create energy out of nothing. You take the energy out of the active medium and put it in the laser light. An atom amplifier takes atoms out of a Bose-Einstein condensate and puts it into the propagating cloud of atoms. So what we did is, we had a small input cloud. This is sort of the cloud which has passed through. But then, when we activated the amplification using extra laser light, in order to fulfill momentum conservation, we saw a much, much bigger output. So what we could show here is the characteristic of an atom amplifier. This is the number of atoms you put in, this is the number of atoms you put out, and with a gain of 30. So we are now inspired by light, and we do with matter waves what people have done with laser light. And since we just had a wonderful conference here, organized by Professor Bellic on photonics, I should tell you that we are now doing nonlinear atom optics using Bose-Einstein condensation matter waves. Okay, so let me summarize. I hope I could show you that light is fun, light is exciting, but light is also a source, not only a source of energy, but a source of momentum and can provide forces. But light is even more, in the most general way, light continues to inspire science. But I would also say the most important part about doing science are the students and the scientists, and they are inspired by light. And I think if Ibn al-Haytham would be alive today, I think he would smile and he would be very pleased what uses we have now found for light. I thank you for your attention.
Okay, thank you. Yesterday we learned about Ibn Haytham 1,000 years ago, but today we have Ibn Haytham for this generation. Okay, because Wolfgang. Okay, let me open the floor for the question. Okay, if we have a question.
Excuse me. We don't have theory or real practice. Means that we can make a spaceship like sailboat depends on a sail for moving in the space or for motion in the space.
Yes. The question is, can we use laser? Can we use light for the force of light for a sailboat through space? Yeah, I haven't done through the numbers, but in principle it would be possible to have a big area and the force of the sun would take then the sail and accelerate and have a force on it. However, I know from the example of this light mill that you can actually get more force and more momentum out of thermal effects. So in a way, it may be more effective if you're not just using the recoil of the photons, but if you absorb the light, heat up the surface, and then emit some gas. Of course, to emit some gas is the principle of a jet engine, which expels moving atoms. So if you don't have that, if you're really in outer space, then I think your idea of the photon sail should work.
So it's possible.
Huh?
It's possible to be applied.
It's possible. Actually, I'm now embarrassed. I should have, by talking about it, I should have looked up some NASA website or so if this is an option for future space travel or for sending spacecrafts very, very far out, because it is a way of propelling a spacecraft which does not require any fuel. You don't have to have fuel at all. But whether this is just a dream or whether this is within the realms of reality, I should check. But the equations in principle allow it. The only question is the force too small or is it sufficient? Square meter. You remember the square meter and the grain of sand? It's not a lot.
We can.
But
We need a big area or
Yeah.
large area for the sail.
Yes.
Thank you.
Thank you. Is there another question? Sure.
So, thank you so much for this talk. It's fantastic. I've got many questions, but
Just one question.
How can we see if suddenly all atoms became only one body, and how do we detect the temperature of the condensation?
Okay, this is a question about Bose-Einstein condensation. the question is, how do all those particles just form one wave? All I can say is this is quantum physics in action. You do not have to do anything special. You just cool down the atoms, and suddenly it becomes favorable for the atoms because of energy and entropy to form one big wave. This is the natural way how atoms behave if they have very low energy. So it's fascinating, and it has fascinated me as a researcher. It looks so organized to form one wave, to march in lockstep. But once particles, the temperature is low enough, there's not so much energy. You can say if things are cold, the atoms just want to get together into one wave. If you want to use this analogy, they huddle together. And that's what happens suddenly at a certain temperature. And how do we observe it? How do we measure the temperature? Actually, the atoms which march in lockstep have zero entropy, and as such are not associated with the temperature. The temperature is the extra atoms which are not forming the wave. So in other words, it is the thermal component, and not the Bose-Einstein condensate, which determines the temperature of the system. Yes?
I have a question. This question, we know that no the electromagnetic waves are affected by magnetic field and a magnetic force. But you said that we can make the atoms as a dipole.
Yes.
How can I do the neutral atoms as a dipole? The first question.
Yeah. Let me answer that immediately. The question is, how can we regard a neutral atom as a dipole? A neutral atom has a positive nucleus and electrons outside.
Yes.
And as such, if you just look at an atom in isolation, it has no dipole. But if you apply an electric field, the negative charge and the positive charge get separated. It is an induced dipole.
Yes. By extending the electric field, you do it.
You need an electric field,
yes.
But the electric field is, in that case, the electric field of the light. The light is an electromagnetic.
Yes, I know that the electromagnetic waves has two fields. By letting them interrupt each other and propagate in the electrical direction of the two fields.
Yes.
Okay?
Okay. Any question from the student?
I just wanted a short comment. I'm going to speak loud. A short comment is not really agreed and actually realize it's not so to say. I think one was realized about 6 months ago or so. It was launched with a setup. NASA actually participated. And then they released the sale, and this was just a trial.
Okay.
It actually spread, the sale area was about 300 square meters.
Okay, interesting.
And so eventually crashed, but they planned for it to crash. They just wanted to test the idea. And several such tests have been launched before. For example, from Japan, and the last one was from the States. It was, I think, within the last year or so. Okay. So that's my comment. That's all. Thank you.
Thank you.
Thank you. Student?
I was trying to understand what
Use the mic.
I wanted to understand what could be more real for the earthly applications for this. When you mentioned it has zero entropy, does it mean it could be potentially used for something on the stealth side? I'm just trying to understand the Bose-Einstein condensate. If you want to have some real worldly applications, what could be those potentially?
Okay.
Maybe stealth or something.
The question is about applications of Bose-Einstein condensation. Well, I gave you one application of low temperature atoms, and this was improved atomic clocks and improved metrology. Now, for those applications, people are usually quite happy with microkelvin temperatures. The Bose-Einstein condensate at nanokelvin temperature, to the best of my knowledge, has not found so far practical applications. It is a research tool to understand more about materials. So my vision is, if we do research on Bose-Einstein condensates, alpha-cold atoms, these optical lattices and all that, you obtain deeper understanding of materials. And then in 20 or 30 years, it's a long time scale, but it's fundamental research, material designers will be inspired and find new materials which will then have practical applications. So my dream is that somebody may understand, have a better understanding, will obtain a better understanding for superfluidity and superconductivity, and maybe in 20, 30 years somebody finds a better superconductor which is used for power transmission for our country. So that would be a practical application, but it's 20, 30 years ago, and it's not a direct one, it's something which comes through insight and through knowledge. The question is whether we can do Bose-Einstein condensation with any kind of atoms.
Any kind of atoms, and it's something more complicated with molecules.
Oh yeah, that's the first one is, can we do Bose-Einstein condensation with any kind of atoms? Well, I was a little bit cheating here in my talk. Atoms can be bosons or can be fermions, depending on, you know that atoms at a more fundamental level, atoms consist of neutrons, electrons, and protons. And only when the number of constituents is even number of protons, neutrons, and electrons, then the atom is a boson. If the number is odd, it's a fermion. And it's clear there is no third choice, it's either even or odd. And the Bose-Einstein condensate only works for atomic isotopes which have an even number of constituents. But every element in the periodic table, with the exception of beryllium, has at least one bosonic isotope. So therefore, with that, with the exception of beryllium, every chemical element, atoms of every chemical element, can be Bose-Einstein condensed. We have recently extended Bose-Einstein condensation to molecules, and hopefully we can do more complicated objects in the future. The fact is, some atoms are much easier to Bose condense than others because they have a simpler structure. Just take as an example, we need really laser cooling, we need lasers for so many things, and there are atoms which can only be excited with deep ultraviolet lasers, and it would take years to build those lasers. And of course, as a researcher, we pick the atoms where we have powerful visible and infrared lasers available commercially. So we pick usually the atoms based on the technology which is needed, and so there are some atoms which are easier than others. But in principle, almost every atom can be Bose condensed.
Okay. And the one more?
The one we use in our research are all from the first column of the periodic table. The results I showed you were mainly sodium, but we also use rubidium and lithium isotopes.
Thank you. Any more questions? No? Okay, thank you. Thank you.